John Buck back with another video for ECE 320 Discrete Time Linear Systems for UMass Dartmouth. Today in this video I'm going to tell you about properties of convolution. Specifically, convolution and addition have a commutative, distributive, and associative properties the same way we have with normal algebra with addition and multiplication. And these properties turn out to be very efficient, are important in making efficient signal processing algorithms, being able to exploit them the right way. So it's important not only to sort of know them in a trivial pursuit sense that you can answer what they mean, but to get fluent using them as we head into the rest of the semester. Okay, so again, our topic for today are convolution properties. And we're going to talk about each of these in the mathematical sense, and then I'll connect it to what it means for system diagrams as well. The first and simplest one is the commutative property, which says that if I have x of n convolved with h of n, I get the same thing if I take h of n convolved with x of n. And again, good point to remind that we use the little star here to say that these two things are convolved. It's also an important confusion many people have early on, and maybe an understandable one, because convolve is an irregular verb. We do not say that two signals are convoluted. Convoluted means two things are complicated. Well, if we say I take two things and I perform the operation of convolution on them, I say they were convolved. And so in the equation sense, it says it doesn't matter which order I put them in, I get the same answer. What that means that's kind of interesting for systems is that if I take the input and the impulse response and switch them around, I also get the same output. So it doesn't matter if x is the input and h is the impulse response, or if h is the input and x is the impulse response, I get the same thing. So that's the commutative property. The associative property says, tells me if I have x convolved with h of n, and then I take h1 of n, I take the answer of that, and go convolve it with another signal h2 of n, that I get the same answer, x of n, as if I convolved the two h's first and then convolved that answer with x of n. So I can associate a chain of convolutions in any order I want. Sounds kind of dry when you write it like an equation. Where can you take this to the bank in an engineering system? Well, what this tells me is if I have a cascade connection of two LTI systems, I get the same result if I take the two impulse responses, H1 and H2, and I convolve those two first, and then I make a new system, just a single system, whose impulse response is the convolution of the two impulse responses that were connected in series above, I'll get the same answer. So sometimes this lets me make one system that's much simpler that I can implement faster or with less latency. Sometimes it actually goes the other way. Sometimes I look at a complicated system, and if I can think of how to factor it, a special kind of factoring called deconvolution, we'll talk about later, I could go back and break it into maybe two simple systems that I could run in a pipelined architecture much faster than the one big complicated system. So the ability to move back and forth here is really important. The ability to get as fluent as we can sort of shows a deep mastery of the concepts and is often the key to developing efficient signal processing projects in real life or implementations. And the third one that falls along these lines is a distributive property. In the boring equation form, the distributive property says if I take x and I convolve it with a sum of two impulse responses, so if I have h1 and h2, that says, well, I get the same thing as if I convolve x with each one of them first. So I convolve x with h1 and I convolve x with h2 of n, and then I add them. So again, turning that into systems, what's going on here is saying, well, I've got the second equation is this system below, right? The top branch is x convolved with h1, that's my output. The bottom branch is x convolved with h2, and then I'm adding them together. What the distributive property says is I can represent this system by something, or it's the same result if I draw something that's like the left-hand side. So it says rather than implement the two systems in parallel, I could take the two impulse responses and add them. And I'll get exactly the same result. So again, not too hard to imagine how this leads to some efficient computations or simpler computations. Sometimes I'll look at a parallel combination that's taking up 2 threads on my CPU or maybe 2 cores on my CPU and say, you know, I could just add those 2 impulse responses and do it together and only need 1 core to do it. Sometimes I can go the other way too, though. Sometimes it turns out to be very helpful to take one big complicated system and say, well, you know, if I think about this, I could break it into the sum of 2 pieces and put each of them on a smaller piece of hardware running faster or give me less latency or something like that. So one way or the other, it's being alert to opportunities to apply and exploit these things often is the key to making really good, either really good signal processing algorithms that exploit or minimize the use of some scarce resource, whether it's memory or time or latency or CPU cores. They can all be important that way. Okay, so again, to finish up, 3 properties today for convolution. Convolution, we have a commutative property, which says I can convolve 2 systems in either order. I have the associative property, which says if I have a chain of just convolutions, you know, X convolved with H1, convolved with H2, I can group them in any order and I'll get the same answer. And that tells us things about combining series connections. And then we have the distributive law, like we just saw, that tells me that if I have a convolution with the sum, I can convolve with each piece independently and add afterwards. And that tells me things about parallel combinations. So again, those are 3 important properties for convolution we'll be using often this semester to make for efficient systems. All right, that's all for this time. I'll see you in the next video.